My name's not on there. That was dumb. I'm Andrew Hirsch. I'm a postdoc at the Max Planck Institute for Software Systems. I work with Deepak Garg. And I'm going to tell you about a problem that he and I have been thinking about along with Ethan Cacchetti, who's in the audience, and I think we'll be giving another short talk on unrelated things, about reasoning about effects in information flow type systems. So I kind of want to just start by thinking about a very simple program. It's one that those of you that do information flow should be kind of familiar with. This is a program that just is assigned x either 0 or 1, depending on h. And the only problem comes when h is a private Boolean, so an adversary is not allowed to learn about it, but x is publicly observable. So an adversary can read x, and now they've learned the value of our private Boolean. And if we're, so this is an example of an implicit flow. And then an information flow control world, where we're using type systems to reason about information flow, we reason about this sort of program using a program counter label, which is an abstraction about how much effects we have, essentially. What can an observer learn from observing the effects in this program? But it's not the only way to reason about effects in a type system. Instead, we could go to a type and effect system. So instead of labeling this with a information flow label PC, we're going to label it with an effect label W. So we say that this program might write to some outputs. And this sort of system is actually used by compilers. Optimizing compilers use type systems like this in order to do things like do optimizations on effectful programs. So if we're reasoning about our programs using these PC labels, and we're then optimizing them using these type and effect system labels, you'd really hope there was some connection between those. And the question I really have is there? So let's look a little bit more deeply about what that would mean. So let's think about the semantics of a program like this with some information, with some type and effect system. Well, the way we give this semantics is via monadic translation. So we can translate this effectful program that writes to some output as a monadic program that now accepts an input state and returns a pair of the return value plus the output state. And this is well known to be an equivalent way of reasoning about programs as these type and effect systems. So the interesting thing about this program, this translation, is it's completely about the effects. It doesn't reason about information flow labels at all, and importantly, it doesn't reason about the program counter. But without using a program counter at all, I can prove that this translation type checks in an information flow control safe language, a non-interferent type system, if and only if the effectful one does with this program counter. And when I realized this, I found this rather disturbing because the program counter is nowhere. It seems to have just disappeared, even though it's vital for our original reasoning. So if you go out and try to prove this, as opposed to just looking at it intuitively, you do end up using an invariant about the program counter in this, which is if you have a write, then your PC is high enough. Your PC is sort of high. And so what we'd like to be able to do is we'd like to be able to work in the semantic framework that monads give us to be able to understand what these program counters really are doing from a type and effect system point of view. And in particular, if not only can we find a monadic translation of an effectful program, but given a monadic translation, there's actually a well-known correspondence back to effectful programs. And what we'd really like to be able to do is to actually find a monadic translation back using this invariant that gives us a way of reasoning about these program counters. So in other words, if you give us a semantics for your effects, we'd like to be able to get an IFC system back using this standard monadic semantic reasoning. And this would tell us a lot about how these PCs work and give us a new way of building IFC systems for languages with other effects. And with that, I would thank you.
Questions?
So the PC label, you say it's for effects other than control flow effects?
No, it's used in reasoning about effects and control flow, right? So in particular, we often use it to reason about input-output or about state. You can use it to reason about non-termination as well. So these are all classic examples of effects, but there's a lot of other effects that we can think about. So non-determinism might be another one that we might want to think about, or probabilistic non-determinism. These are all things we might want to design information flow control languages for. Currently, if we were to do that, we'd have to sit here and handcraft the PCs. We have some intuition about how to do that. I'd like to build a mechanism to do that.
So I'm also curious that if you went through this process, would you end up effectively having some sort of monad in the PC, or store the same information in the PC that you had in the original?
If I understand the question, would we be able to basically regain the same PC we started with? If we kind of go PC system to monadic system to PC system. Is that your question?
Somewhat.
I suspect so, but I don't actually know. I suspect if not, it's going to be because we're going to be less precise.
Okay.
So there are all these standard type and effect systems. Can you use like one of the existing ones to reason about PC?
So in our example languages that we've built so far and been playing with, we have completely standard type and effect systems. They happen to operate on a language that has some information flow labels, but the type and effect system doesn't care about that.
Other questions? Okay, thanks Andrew.